So we have learned what is a function is continuous, and we also know what is a function is differentiable. So what is the relation between the continuity and the differentiability? So here is the theorem tells you the relation. It says if a function f is differentiable at x equals c, then this function must be continuous at x equals c. But the reverse is not true. So now let's look at the remark. So that means differentiability will imply continuity, but the continuity cannot imply the differentiability. So in other words, differentiability is a much stronger condition than the continuity. So now let's look at an example tells you why the continuity cannot imply the differentiability. So this is the example for a function we are very familiar with, which is f of x equals the absolute value of x. So we want to show that this function is continuous at the point x equals 0. So this one is continuous. So how to find? So we want to show it's continuous. This one is continuous at x equals 0. So how to show that? Do you remember the definition for the continuity? Which is if you take the limit x approaches 0 of this f of x, we want to know if this one is equal to f of 0, right? If it's equal to f of 0, then we can see it's continuous at x equals 0. So now let's look at this, the left side. So this becomes the x approaches 0 of the absolute value of x, right? So when we take the limit, the first step is you try to plug in the number, right? So here plug in 0. So yes, we can do that, right? There is no problem. So which is equal to 0. And we also know f of 0 is also 0, right? So that means this limit x approaches 0 of f of x is equal to f of 0. So this function f is continuous at x equals 0. So next part, we want to show that this f of x equals absolute value of x, which is not differentiable at x equals 0. So that means the derivative does not exist. Okay, so we need to check the derivative at 0. So from the definition, we know the derivative at 0. So here, from the definition, we know the derivative of f, which is equal to the limit h approaches 0 of f of x plus h minus f of x divided by h, right? So now we want to know what is the f prime of 0. So we replace x with 0, so it becomes, because it's a function of x, so you can plug in x equals 0, so this would be f of 0 plus h minus f of 0 divided by h. So it's equal to h approaches 0 So this is the denominator. So what is f of 0 plus h? F of 0 plus h, which is equal to f of h, right? F of h equal to what? Which is equal to absolute value of h, right? So because f of x equals the absolute value of x. So you just replace x with h, right? So you will get the absolute value of h. So what is f of 0? F of 0 equals 0, so it's minus 0. So at last, you will have the limit h approaches 0 of the absolute value of h over h. One thing, you cannot plug in 0 directly, right? If you plug in 0, you will have 0 over 0 form. So that means we need to modify, right? When we talk about the finding the limits analytically, we have a very similar problem, right? So when you have the absolute value, so you need to get rid of the absolute value, right? So the first thing, you cannot cancel out h directly because this one, on the top, the h is inside the absolute value. You can do nothing inside the absolute value. So the absolute value, two vertical line, like a door. The door is closed. You can do nothing for something inside the door. Okay. So what we should do? So we use the definition of the limit. So it means you need to find the limit h approaches 0 plus of this function. And you also need to test h approaches 0 minus of this function to see if they are the same number, same finite number. Okay, so now let's do the calculations. This is the one-sided limit. H approaches 0 plus. So that means h is positive. So when we do the calculation about the absolute value, so the first thing you need to do is get rid of the absolute value. Okay, get rid of the absolute value sign. So this would be, we use this facts, I put it here, the absolute value of h, which would be equal to h when h is positive, equal to negative h when h is negative. Okay. So when h approaches 0 plus, that means h is on the right side of 0. In other words, h is positive, right? So the top becomes h over h. So it's equal to, so let's simplify. You still cannot plug in 0, right? But you can divide out, becomes 1. So the limit of a constant is this constant 1. The similar thing for another limit. So the denominator is h. What about the numerator? H approaches 0 minus, that means h is negative. So the negative, so the absolute value of h is equal to negative h. So it's equal to negative h. Then you cannot plug in 0 directly because it will still be 0 over 0 form, but you can simplify negative h divided by h would be negative 1. So the limit is negative 1. So you see, these two are not equal. Okay, they are not equal. So in other words, so the limit h approaches 0 of the absolute value of h does not exist. i.e., in other words, the derivative of this function f at 0 does not exist. So in other words, not differentiable. At x equals 0. Okay, so now let's look at the remark for this function. Why this happened? So let's look at the graph. So the graph for the function y equals the absolute value of x, if you check your pre-calculus, it's given by this curve. And when x equals 0, which is here, right? So it says it's continuous, no problem, because you can draw the graph without lifting your pen. But at x equals 0, at this point is a sharp point. So in other words, the derivative at a sharp point or sharp corner does not exist. So for example, if you have this curve, at this point, the derivative not differentiable at this point. It can be differentiable at other points, but not differentiable at this sharp corner.